All right. So remember to know how to do your conversions from degrees, minutes, seconds to decimal degrees, or from decimal degrees to degrees, minutes, seconds. I got to be honest with you, other than me asking that, everybody on the planet just uses decimal degrees, unless you're in cartography or you're using GPS, formal GPS systems that do degrees, minutes, seconds. But it's pretty, I mean, I'm not going to say it's obsolete, but in my world of math and probably your world of math, unless you get into some charting and whatever mapping kind of degree or occupation, I doubt you're going to be using degrees, minutes, seconds much. So most of the time, if you're going to convert, they're going to give you something like, hey, what is the sine of this angle? And they'll give you a degrees, minutes, seconds. You're just going to need to know how to convert that to decimal degrees so that you can take the sine of it. Or at the very minimum, know how to enter it so you can take the sine of it. All right. But moving beyond that, just make sure you know those definitions. Every year, I'll put on the test. And I think I give you a big review sheet kind of in the middle of this. If you look down there, something like next Tuesday, I'm going to give you a review sheet and a take-home test that will be due Friday. So you'll have like a few days to kind of fit it in along with your other homework. It's not an overly big deal. Probably take you, 30 minutes on the review sheet, maybe 30, 40 minutes on the quiz. But I know it's a little bit extra, but I'm trying to make sure I can fit everything in this year. And since we lost so much with the stupid red-blue stuff, I'm still trying to catch up and make sure I can not jip you out of material like you lost last year and my kids lost last year. So anyway, that quiz will be on there. So you'll probably see it again then. But the real quiz, the real test that you have will probably have a question or two out of the 25 questions that ask you about a couple definitions maybe, or about converting. So just make sure you can do it. So today, I want to talk about the 6 trig functions. Now, yesterday I mentioned at the very beginning, when you see a trig function of an angle, like sine of a theta or tangent of a theta, what does that really stand for again? I mentioned it yesterday. It's a something over something, or a ratio. It's just a ratio of 2 of the sides. And the angle is just telling you, hey, what kind of a triangle do you have? Because if it's a right triangle and I tell you it's a 30-degree angle, well, you know one of them is already 90, right? So that would be 30, 90, 60, or 30, 60, 90. Right? If I tell you this one's 20 degrees and it's a right triangle, then 20, 90, 70, right? Because the complements. So all 20, 90, 70, all 30, 60, 90s, all those triangles, no matter how big or small they have, the ratio of any 2 comparable sides, like opposite adjacent, opposite hypotenuse, whatever, any of those, the ratios will always be the same, even though the sides may be bigger. Does that make sense? It's kind of like when we talked about directly proportional, right? When we said directly, you kind of put x over y. Well, these are all directly proportional, but they have names. So I think did y'all learn this with Helmers last year? Have I asked that already? Did you learn the 6 trig functions with Helmers? Or the SOHCAHTOA? That's the 3. Did you learn anything about cotangent, secant, and cosecant too? Okay, let me just review those. And then you need to start disciplining yourself out of continually thinking opposite, adjacent, hypotenuse. I want you to start thinking y, x, r. And I'm going to throw this up here. So if you were wise, you would write all this down. But again, that will be up to you. So sine, and I'm going to continually refer to these. Sine, and by the way, it's not sine. That'd be like me saying log. Hey, what's the log? What is it? What are you thinking when I said it? What's the log? Not what does the logarithm mean? Literally, I want you to evaluate this for me. What is the log? That doesn't even make sense, does it? Like, I would have to ask you, what are you logging? What is the log of 3? Oh, well, I can type that in my calculator. What's the log base 2 of 4? I can figure that out. But I have to be logging something, right? So I never say something like sine is opposite of hypotenuse. It's the sine of the angle. Are you with me? It's really important that you get that down. The sine, you don't say sine is opposite over hypotenuse. That's terrible form. That's like saying the log is 2. The log of what is 2? Right? The sine of the angle that we're talking about. So if I had a triangle, let's just say I had this right triangle, and we're talking about that angle. theta. Then the sine of this angle theta would be the side opposite it, which would be this one, over the hypotenuse, which would be that one. And we call the other one, not the opposite, not the hypotenuse, we call that the adjacent side. So sine is defined as opposite of hypotenuse. Now, what is cosine defined as?
Or adjacent over hypotenuse.
It's adjacent over hypotenuse. Now, guys, before I go too far, that's the sine of theta. The sine of this angle that I'm pointing to right now, which I haven't really given a name, let's just say it was beta. Is the sine of beta still that opposite over this hypotenuse?
No.
No. If I'm talking about this angle, the beta, then that would be the opposite. So make sure you understand that too. I mean, that's something that usually is understood, but we're talking about with reference to the angle we're talking about. Now, most of the time when I'm giving information or I'm using trig, I like to think in standard position. And what do we say standard position was? Yeah, when one of the sides is pointing at 0. And you can see one of these sides right here, if you think about this angle, if you kind of extended it, you go, oh yeah, that's pointing at 0, and then this is pointing up at some other angle up here. I'm just labeling it right here. Y'all tracking with me? Okay, so cosine is the adjacent over the hypotenuse. And then what is tangent of the angle? Opposite over the adjacent. Now, did you also know opposite over the adjacent? Did you also know that sine was that tangent was the sine of the angle over the cosine of the angle? Did you know that? Because what is the sine of the angle? Up over height, right? So up over height. And what is the cosine of the angle? Adjacent over height, right? And what happens if I multiply by the reciprocal? The heights would cancel and you have up over adjacent. So that's something to remember too, that a tangent of an angle can also be found if you know the sine and the cosine of the angle. You can just put the sine over the cosine. We'll get back to that later. All right, now, there are 3 more that don't have a nice clever thing like SOHCAHTOA, but I'll talk about some clever things. You can do whatever. So rather than the SOHCAHTOA stuff, the cotangent, right, not the cot. I always have people going, the sin of theta. I don't know that theta has committed any sins, but or the cos of theta. Don't do that. That's like it'll end up rearing its ugly head down the road. Like you'll be in a college class and you'll get asked to do a problem on the board or whatever. And you'll walk up there and you're like, all right, the cos of theta, and everybody's like, and they'll mock you publicly. So don't do that. Learn to say cosine, tangent, sine, cosine, that kind of stuff. The cotangent, not the cot. Right? The cotangent of theta happens to be the reciprocal of the tangent. So it's tangent's reciprocal. So I'm going to kind of connect those in this way. And then there is the secant of the theta. The secant of the theta just happens to be the
opposite of the cosine.
Well, not opposite, but reciprocal of the cosine. So, hypotenuse over adjacent. And then the cosecant of the theta happens to be the reciprocal of the sine, which is the hypotenuse over the opposite. And there are, yes, clever little things like this. People remember these like this is so. Sine equals opposite of hypotenuse. And then cosine equals adjacent of hypotenuse. And then TOA, tangent equals opposite over adjacent. I don't know of any for these, but reciprocal, reciprocal, reciprocal. But there's also some old hippie caught another hippie tripping on acid, and you can go on and on and on with dumb little things people come up with. All right?
Interesting one.
And then my personal favorite oh, 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 oh. But again, whatever works for you. All right? So that's if you know them in this order. And I kind of have them burned in my brain in that order, but that doesn't mean they're going to show up in their book in that order. A lot of times in the book, it's like sine, cosecant, cosine, secant, or whatever, and they'll scramble them up. But if you have them sine, cosine, tangent, cotangent, secant, cosecant, then that little pattern works, and these are reciprocals. And if you're ever wondering in your head, why did they make sine and cosecant? The names are just made up, right? We talked about that. It was just a name given to represent that ratio. Well, why didn't they make the reciprocals sine, cosine? That seems like it would make more sense, right? To put them together like that since they're reciprocals. And why didn't they make like these reciprocals, like secant, cosecant, since they're reciprocals? Well, they actually are put together. Sine and cosine do go together in another identity. So there is a reason why it's sine and the cosine, and I'll get to that later today. Now, what I want you to learn is this. We're about to crank out this thing called the unit circle, which I'm guessing you didn't do last year. Have you ever even seen it or heard of it? Some of you have? Okay, some of you have not.
It was on the homework.
I put it in the homework last night? Okay. If I did, that very well could be an accident based on you normally learn that with Helmers. But again, you guys got gypped out of a couple of months of stuff, probably. So, what you're normally doing, this unit circle we'll talk about tomorrow, I believe, organizes all this information we're going to talk about today into a table. And it really helps your brain kind of get it all organized so you don't have to memorize stuff or draw too many pictures. The unit circle is the picture of the special triangles. And you know something about special triangles because you learned ratios of special triangles in geometry. Y'all remember this? Y'all with me? Y'all remember like 30, 60, 90 proportions and 45, 45, 90s? So if you remember those, great. That'll help you on this unit. But all that information is organized into this table. And if you memorize the table, which I'll show you a lot of tricks to doing that, it's really easy to answer questions like, what's the tangent of 300? And you can go, oh, from my unit circle, swing to 300, put the y over the x, you're done. But this is how you have to be able to think to be able to use your unit circle well. And that is, you need to kind of think of this angle, or I'm sorry, this triangle as being on an x and y axis. Okay? So if the triangle was on an x and a y axis, this adjacent movement would be like me moving along x. So when I think adjacent, I think x movement. So anywhere where I see an adjacent, I have to think x. Right? And then anything moving up, I need to think y. So this opposite, I need to be thinking y. And then you're going to see this with the unit circle. On the unit circle, we're going to take this hypotenuse and we're going to shrink it down to a length of 1, and we're going to rotate it all the way around. So it's going to act almost like the what? The radius. So the hypotenuse is going to act like a radius. So we're going to call the hypotenuse r. And if you can think this way, in terms of x, y, and r, instead of always thinking the opposite hypotenuse and adjacent, it's going to help you when we get to the unit circle. It's going to really help because the r value on our unit circle will always be 1. That's why we call it a unit circle. Like it's literally 1 unit long. And we can use that, again, we can use that even for bigger looking triangles because the ratios are always the same. Whether it's a big triangle or a small triangle, if an angle is an angle, then whether it's, you learn that in geometry, right? Similar triangles, the ratios of the two sides are always equal. That's what trig's all about. It's looking at ratios. Okay? And the great thing about that now, instead of, if I don't know the sides, but I know the angle, I can type cosine of 20 in my calculator. Guess what it spits out? I mean, not the number, but what number it spits out represents the what? The ratio. So like if I type in cosine of 20 and it spits out 0.6, that tells me, oh, the ratio between the adjacent and the hypotenuse is 0.6. So it's just another way of doing it where I don't need the sides anymore. All I need is the angle. Still gives me the same thing because cosine of the angle is the ratio. But anyway, enough of all that. So make sure you know these representations as well when we get to the unit circle, because that's going to become important. All right, the next thing I want to talk to you about is this. What if I had a 20, 70, 90 triangle? And I'm going to label this X, Y, and R. So I like X, Y, and R also better, because if I start talking about angle 70, I don't see this word adjacent there kind of annoying me, because in terms of 70, this would be the opposite of 70, wouldn't it? Whereas if I'm talking about 20, that's the opposite. Well, now I don't see the words opposite and adjacent anymore. I see X, Y, and R, and I can just use my formulas. So let me ask you a question. What if I were to ask you about the sine of 20 degrees? What would you say that the sine of 20 degrees was?
Y over R.
The opposite over hypotenuse, the Y over the R? Okay, so I'm going to write Y over R. Now, what if I were to ask you what the cosine of the 70 is? Look at 70 right here. What's the cosine of the 70? Wait a minute.
Y over
Cosine is what? Adjacent over hypotenuse. Now,
So it's Y.
if the angle is here, it's X over R. But if the angle's up there, it's what? Adjacent over hypotenuse. Relationship between that 20 and that 70?
No.
So they are?
I forgot what it was called.
45.
What?
No, yeah.
Getting closer.
Complementary.
Complementary? They're complements of each other. Think about it. What if that's a 10? If that's a 10, that would have to be an 80, right? 10, 80 plus 90 is a total of 180. So if that's a 10, this would be an 80. Still complements. Well, there's this identity that says this. The sine of any angle is the cosine of what? How do you think I say complement? Do what? 90 minus theta. Think about it. Sine of 10 is cosine of 90 minus 10, which is cosine 80. Sine of 20, cosine of 90 minus 20. Sine of 50, cosine of 90 minus 50. This is how sine and cosine are related. So the sine and the cosine are related by this rule. And this is called the cofunction identity. Except there are more than one identities. And they don't just work with sine and cosine, they work with cosine sine, which that's a little obvious. But they also work with tangent, cotangent. By the way, also, when you write a degree, you got to put a little open circle or put a dot. I get a little sloppy, just put a dot. But you got to see something up there representing the degree sign. They also work with cotangent and tangent. So you can flip them around as long as it's one and the other. Secant theta, cosecant 90 minus theta. Cosecant theta, secant 90 minus theta. Now, how do you see that on a test? Examples. Secant of 15 degrees equals cosecant of blah. And you go, wait a minute, how are secant and cosecant related? They're not reciprocals, right? Oh, the cofunction identity, 90 minus 15, 75. The cotangent of 12 equals the tangent of, and these are actually reciprocals. But, so that means the cotangent of 12 would actually be equal to 1 over the cotangent of 12. But we'll get into that later. But how are cotangent and tangent related?
78.
90 minus that, 78 degrees. Or even a trickier one. The cosine of negative 15 is equal to the sine of 105. Because they are 90 minus a negative would be plus 105. Y'all seen it? Cofunction identities. And also, as we get to radians, do y'all remember that 0 degrees was pointing here? And then if I went halfway around, what was that?
180.
180. Or what would that be in radians? Do you remember? Pi. So what would, if I go half of 180, it's 90. What is straight up in radians?
Pi over 2.
Pi over 2. So occasionally, instead of seeing 90s right there, you'll see pi over 2, 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 pi over 2. And those are a little trickier if I said something like the sine of pi over 3 equals the cosine of, well, you can't go 90 minus pi over 3 because that's mixing up degrees and radians, right? So what would you do? Pi over 2 minus pi over 3. And then you'd have to simplify that and get pi over 6. All right, find the common denominator, subtract. So that might be a little trickier, but if I'm totally honest with you, not very common in this course. So far, so good? Okay, moving on. Special triangles. Now, you should know this, but if you don't, no harm. There's just harm in not learning them if you don't know them. So there are 3. That's it. So the first one, probably the most common. Well, I don't know if that's true. 30, 60, 90 triangle. The 30, 60, 90 is what we call those. Has a definite proportion. And do you remember what it is? The short side is 1A, or I'm just going to put a 1.
2, 3.
The long side is 2. You could say 1A, 2A. And then the middle is root 3 or A root 3. But for our purposes, since it's proportions, I'm just going to write 1, 2, root 3 for now. Okay? But if you want to write A, 2A, A root 3, knock yourself out. All right? That's a 30, 60, 90. Is that really any different than a 60, 30, 90? No, except the 60, 30, 90 is kind of sitting up a little taller. All right? That would be the 60. Then this would be the what? The 1. The hypotenuse would be the 2. And that would be a root 3. So really the same thing, but just turned on its end. And then the 45 is the isosceles right triangle. So a 45, 45, 90. All right. I'll go back and put a 30 in there. So 45, 45, and 90, what are the ratios here?
1, root 2.
Root 2. Tomorrow when you do the unit circle, I literally am going to take these 3 triangles and I'm going to mark them off in a circle. Just kind of draw them in there for you. And we're going to take this information and turn it into a nice, neat table that we can use. It'll really going to help us simplify what we're doing today. But today I'm going to labor through this crap. Okay? So what if I threw at you right now, hey, what is the sine of 30 degrees? Well, since you know, now if I said what's the sine of 31, you're not going to know. I don't know what the ratios of a 31 degree, a triangle with a 31 degree angle. I have no idea. I know they're close to the 30, but they're not exactly the 30. So if I said sine of 30, couldn't I go to this and do what? Opposite of hypotenuse, or y over r? Take the 1, put it over the 2, no problem, right? What if I said, hey, I want you to find the cosine of 60? How do I find the cosine of this 60? Right? I do adjacent over the hypotenuse. What if I said, hey, I want the sine of 45? Sine of 45, what is it?
1 over 2.
1 over root 2. And then because it's algebra 2, we got to always rationalize the denominator, right? What if I say, hey, give me the tangent of 60? 60.
Root 3.
Root 3 over the 1, which is just root 3. What if I said, what is the cotangent of 30? If tangent is opposite over adjacent, which most people have that down with the TOA, then the cotangent's just the reciprocal, right? So if you need to do that, if I'm finding cotangent of 30, I very often find the tangent of 30, 1 over root 3, flip it, root 3 over 1, because that's the relationship between cotangent and tangent, right? So root 3 over 1. Are you with me on how I can use these? Now, what's going to be helpful tomorrow when I do the unit circle is what happens when I say, what's the sine of 90? It's kind of hard to do a sine of 90 because there is no, like if I say the sine of 90 and there's my angle, that opposite's the hypotenuse and it totally scrambles everything. So it kind of breaks down. But really what I'm asking you to do is take this, visualize this. I'm asking you to take this and continue to open up the angle. Now, as I open up the angle, what's happening? That side's getting smaller and smaller. What do you think happens as I finally get straight up to 90? It shrinks to 0, which is a little bizarre, right? And annoying to think like that. So what that means is my adjacent side literally just shrunk to 0, but my opposite side is now the same thing as my what? Same thing as my hypotenuse. And this does not make people happy. Same thing about going to 0. What happens if I have this and I start shrinking this angle to 0? What do you think happens to the adjacent side? I mean, sorry, to the opposite side?
Smaller.
It becomes 0, right? And then what happens to the adjacent and the hypotenuse? It becomes the same. That really bothers people until they get the unit circle. And the unit circle, you have all these little values that you've labeled and memorized. And anytime somebody says tangent of 90, you go to your unit circle, whether it's on your paper or burned into your fibers of your brain, which is where I hope it's going to be. You just go there and you go, oh, and you grab the two values and you're done. Really eases the pain and suffering of overly thinking about odd situations like 0 and 90 and 180. But tonight you're going to be asked a whole lot of stuff about 30s and 60s and 90s and that kind of stuff. You're also going to be asked questions like this. And again, you're going to be using all of this information to do it. Hopefully it will not be too bad. So hypothetically, hopefully you got all that down. What if I said, determine the 6 trig functions. All right, determine the 6 trig functions. Make sure you know the wording that I'm writing up here. Of an angle in standard position. What does that mean? What about 0?
Like the unit circle 0.
So one of the arms of the angle is at 0. We usually call it the initial side, but whatever. So it's in standard position, and it's going through the point 37. Now let's visualize this. An angle in standard position would have to have one side pointing at 0, right? And then the other arm would have to be going through the point what? 37. So let's just say that's 3 and that's 7, and there's a point up here. So the other arm is going through that. Now, do you off the top of your head have any idea what this angle is? I don't. But they want me to find the 6 trig functions of that angle. So they want me to find the sine of the theta, the cosine of the theta, the tangent of the theta, the cotangent of the theta, the secant of the theta, and the cosecant of the theta. And again, don't forget to write the theta. Now, does it matter how big I draw this triangle? I'll get back to that in a second.
Wait,
Hold on, not coming. Does it matter how big I draw my triangle? No, because it's going to be this proportion, right? So why not use the 0.37, right? If I use the 0.37, what do I immediately have?
You have your opposite.
I have my adjacent side and my
opposite.
opposite side. And how then could I find the
Basically,
hypotenuse?
Pythagorean theorem.
Pythagorean theorem. So to find the r, or the h, whatever you want to call it, I'm just going to say if r squared equals 3 squared plus 7 squared, all I got to do is square root it, right? And I get 9 and 49, which is root 58. That doesn't look familiar, so I don't know that I can. It's 2 times 29, so nothing comes out of there, right? So that tells me all the 3 sides. And if I have all the 3 sides, can I find all the values of the trig functions?
Yep.
So the sine of that angle would be
7 over root 58.
7 over root 58. Can I leave it like that?
Yeah. No, you have to simplify the bottom.
So 7 root 58 over 58. And while I'm at it, is there a reciprocal of sine somewhere on the board? So why don't I just go ahead and write out root 58 over 7 and be done with it? Right? Cosine.
Wait. Oh.
Because remember sine and cosecant are just reciprocals of the 2 sides?
Cosine is
So cosine is
over root 58.
adjacent over hypotenuse, or x over r, so 3 over that. And I got to still rationalize though, right? And while I'm at it, why don't I just take care of secant? Root 58 over 3. Why didn't I flip my final answer down here?
Then you have to rationalize.
Because I'd have to rationalize it again, and that'd be stupid, right? So just flip this, and then it will be pretty down there. And then how do I do tangent?
Opposite over adjacent.
So 7/3 and 3/7 for cotangent. Not too bad. That's something you'll see. Here's something else you'll see, and this is going to feel maybe a little bit more like geometry. You'll see something like, this is tonight. They'll say, all right, if you have a triangle with this given information, do you see how this is like geometry?
Yeah.
If you don't, remember what you know about every 45, 45, 90, right? Every 45, 45, 90, what do you know?
C is
1 root 2, right? So you got proportions. I'm literally saying right here, I'm going, wait a minute, if these proportions hold, then C over 9 is the same thing as what? Root 2 over 1. So to find C, I could say C over B, but that gives me 2 variables. But I can say, hey, that C over 9 is the same as that side, because that's the proportional side, I mean the same side, that root 2 over 1. And then I can just cross multiply or use my slide rule, slide the 9 up there, C equals 9 root 2. Now, if you're really on your game, you can do better than that.
Don't you just know that 9's A, so just A root 2?
Yeah, that's what I was going to say. If you know these proportions, you know I can always find the hypotenuse by multiplying this by a root 2. So you can multiply that by a root 2. How do you find B?
9.
Yeah, 45 degrees, right? You know that those are always equal. Those are proportions that you know. And if you didn't notice that, you might be fine. Right? I would just say B equals 9 on this. Sometimes they can be trickier though. What if I gave you, and it's not super tricky. What if I gave you something like this? And I say, what is A? Sorry, what is A? What is B?
Use A is.
Okay, but what are you doing when you do this?
You just do the regular proportion.
So you know about your 30, 60, 90. You know that it's 1, 2, root 3 on a normal 30, 60, 90. So you're literally saying, hey, I know the b is always half that. If you can do that, it makes it really nice. But what you can say, oh, then, because it's always half that. So I know that b is my 8. And then what do you know about this side? It's always that times a root 3. So now that it's 8, 8 times a root 3. And you can navigate it that way, or you can just set up a proportion and say a over 16 is the same thing as root 3 over 2. And when you multiply and slide it up there, you get 8 root 3. But again, this should feel like geometry. The only major difference, it really is geometry. It's just trigonometry. It's a very similar relationship. It's just focusing on the triangle ratios. Now, here's probably the trickiest thing, and I think that I will still probably bore some of you. What if I told you this? Hey, sine of an angle is 3/5. Determine the other 5 trig functions. So what am I essentially telling you here? That there's some angle who's what? What's sine of theta mean? So I'm just giving you two sides, right? So I'm telling you there's some angle whose opposite side is 3 and whose hypotenuse is 5. And if I can draw a picture, what can I do to find that missing side? Pythagorean theorem. 5 squared equals 3 squared. Now, hopefully you know that this is a triple, right? 25 minus 9, 16. Square root both sides. Technically, you get plus or minus 4, but clearly I'm going to the right. But that will be a big deal tomorrow when I start moving these out of the first quadrant. You know, when you solve this, you get plus or minus 4. Just negative 4 clearly wasn't an option. But if it was over here, then negative 4 would be the option. So just make sure you're careful about that. So now that I know all the sides, I already know sine, right? But now I can find cosine, tangent, cotangent, secant, struggling, cosecant. Hopefully you know sine and cosecant even if you get stuck, because that's just a reciprocal. But what am I going to get for cosine? 4/5, which means secant is 5/4. And if tangent of the angle is 3/4, then the cotangent of the angle is 4/3. And they're not always going to be pretty. What if I gave you this same question, but I gave you the tangent of the angle is 2/9? Same question. Think about what I'm giving you. The tangent of the angle is 2/9. What does that mean? That's true, but what does that mean in terms of the triangle? Because I'm going to have to find all of them. So if the tangent of the angle is 2/9, the opposite is a 2. The adjacent's a 9. Can I find this? And when you do the Pythagorean theorem, you get the square root of 85, which doesn't simplify because that's 5 times 17. So if that's my relationship, what's the sine of the angle? 2 over that, which simplifies to 2 root 85 over 85. And what's the cosecant of the angle if the sine is 2 over that? Root 85 over 2. What's the cosine of the angle? 9 over that. And 9 over that means 9 root 85 over 85. Then what would the secant of the angle be? Root 85 over 9. Which is the hypotenuse over j. And what's the tangent of the angle? And the cotangent, 9x. And you'll notice I'm all stuck in root in the first quadrant. All right, last little thing. I got 7 minutes. Think I can get it in? I'm going to go back to my X, Y, R triangle. And these 3 identities that you're going to see are probably the most important identities that you'll deal with because they're used in tons of proofs. We get to trig identities. That's arguably one of the tougher things I do all year. So I'm going to build these and hopefully we'll have time to get through them. But just hypothetically, I gave you a triangle and those are the sides. Is this true? I'm going to call this theta. X squared plus y squared is r squared. Yes? Okay. What would happen if I randomly chose, and tell me if I can't do this or not, to divide both sides by r squared? Is that legal?
Yeah.
So if I divide both sides by r squared, what happens on the right side? And I get 1. And isn't x squared over r squared the same thing as x over r squared? And isn't y squared over r squared the same thing as y over r squared? And isn't x over r the same thing as cosine of an angle? So wouldn't that be cosine of the angle squared? And isn't y over r the same thing as sine of the angle? So wouldn't that be sine of the angle squared? And whether you know this or not, a long time ago, the inventors of math decided that it was too painstaking to put that in parentheses, but they didn't want to write cosine of theta squared like this because that made it look like what was being squared? The angle. So they put the 2 right there. That's what we do. So I have cosine squared plus sine squared theta, but most people write it with the sine squared first. Sine squared theta plus cosine squared theta equals 1. Now the implication here is it doesn't matter what the angle is. These thetas are the same angle, right? So whether that's 10 degrees or 20 degrees or 30 degrees or 50 degrees or 90 degrees or whatever degrees, if I have sine squared blah plus cosine squared blah, it's always equal to 1. Not too bad? Now, I'm going to write this down. Four minutes. What if, and I could do it from here, but I'm going to do it from here. What if I took this and divided no, I'm not. I'm going to go back to here. What if instead of dividing by r squared, I divided by x squared? Now what do I get here? 1. And isn't y squared over x squared the same thing as y over x squared? What's y over x? So this is tangent squared of theta. Isn't r squared over x squared the same thing as r over x squared? What's r over x? Secant squared. Second Pythagorean identity. Sadly, you're going to have to know these, but you're not going to have to prove them. And last proof, what if instead of dividing by x squared, I divided by y squared? Now, what happens to this? What is x over y squared? Cotangent squared. What is r over y squared? Cosecant squared. That's the last one.
If we are to write like sine theta and then the parentheses then squared, like quantity squared, you can take points off of that.
Yeah, and I know it seems weird, but it's kind of like writing log base e. I know for when you start out looking at it, you're like, but it makes sense this way. It won't take long for you to get comfortable with it. You just got to get comfortable with it. On the front end, it may seem weird, but yeah, don't put the whole thing in parentheses. All right, guys, see what you can do. Actually, on page 9 in the book, I have all kinds of these identities written down. Forgot about that. So you can look up there and see all kinds of these. Some of the ones we have not done yet, some of the ones that we have. You're going to have to know all these eventually. So if you guys work really well with flashcards, it might be a good idea to maybe make some flashcards and really start memorizing these things. Because by the time the test rolls around, you'll need to know. And believe me, this is just the tip of the iceberg. Sorry. They get much nastier. All right, man, that's all I got.
I haven't read one. Just see if it's still one.